Welcome back to another exciting chemistry lesson. In the previous lesson, we learned about electron configuration, and we also learned about the periodic table in the past. And one thing we have to realize is that this right here is the period number, which represent the energy level of S and P sublevel. And now we are going to look at the group number. And we already learned that in the past that this group number 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A, except for heliums, the group number represents the number of valence electron. What is valence? Valence is another word for outermost. So if we look at a structure of an atom, here we have a nucleus, and assume that this is the first orbit with 2 electrons, okay? And now we're going to the next energy level. So as you can see, this would be the outermost, which is another term we use, valence electron. And we learned that the number in front of letter A is also the number of valence electron for all the atoms in that specific group. And now we are going to look at electron configuration to look at as an evidence of how we determine valence electron for each group. Looking at the definition of the word outermost, basically on the edge, right? And we've learned that as we go down, what happened to the energy level? It is also increasing as well. But look at the S and the P. S and P will always have the highest energy level comparing to the other sublevel, because D is 1 less, F is 2 less. So therefore, the valence electron will always be found on the S and the P sublevel. So let's look at an example. Here we have the basic definition again. Again, valence electrons are found in the S and P sublevels at the highest energy level. Now let's look at an example of electron configuration. We have 1s2, 2s2, and we have 2p6 and 3s2. So in this case, what is the highest energy level is going to be? Well, 3 is the highest energy level. And that is on here on the periodic table, 3s2. That is magnesium. And magnesium is in group 2A, as we mentioned right here. So therefore, it has 2 valence electrons. But by looking at the valence electron in terms of electron configuration, we can prove that right there as well. So there are 2 electrons in the 3s, and it has 2 valence electrons. Now let's look at the electron configuration for sulfur. 1s2, 2s2, 2p6, 3s2, and 3p4. And 3p4, as we can see right here, 3, 1, 2, 3, 4. Sulfur right there, right? And what group is it in? It's in group 6A. So therefore, you expect to have 6 valence electrons. So again, there are 3s and 3p. So sulfur has 6 valence electrons because 2 is coming from the 3s and 4 is coming from the 3p4. Now let's try a more complicated problem where we have to deal with the D sublevel. As always, we are looking for the highest energy level. So all of this right here, see 1 all the way to 3, is lower than 4. So the valence electron in this case, what is 4s2 and 3d5? So if we go back up here, okay, so we have 4s2 going down 3d5. 1, 2, 3, 4, 5. That is manganese. So the element is manganese, okay, and it has how many valence electrons? Now, because we are no longer in the group A anymore, we're in group B, so we cannot use the pattern of the number representing the valence electron. So we have to go back over here. What is the highest energy level? Well, in this case, 4 is the highest, and therefore it has 2 valence electrons because of the 2 in the 4s. And in what energy level? In the energy level number 4. And that is how you look at electron configuration as evidence to support the number of valence electrons in a specific group on a periodic table. And as always, if you have any question, take a picture of your work, put in a form, and we will help you from there. And we'll see you next time on another exciting chemistry lesson.